I'm Harry. I've been researching zk-SNARKs for the past year. I'm also a maintainer of a project called EthSnarks, trying to bring zk-SNARKs to Ethereum and figuring the issues out there. So I'm going to try and break this down quickly into like two different parts, which is what are SNARKs? But you've seen a lot of that already. But when do we use them and when does it make sense to use them, especially on Ethereum? And some sort of building blocks that are Ethereum compatible. And then dig into high-level languages, like compilers, what does that look like, and a couple of cool examples. But at the moment, this is where I think we are with SNARKs. It's still very sort of new and dangerous and exciting. But yeah, essentially, you've got this diagram that you've seen thousands of times before. But it sort of hits these four different things: that optimal verification, optimal proof size, it's compatible with Ethereum, and out comes crypto magic at the end. But I like to think of it in a slightly different perspective, which is you've got this SNARK hammer that you can mix public and private variables with in the same chunk of code, and spit proofs out the other side. But I want to focus less on like what you can't do with them, because if you get into SNARKs, you'll find out they'll make your life painful. So instead, I want to look at more like verifiable computation. What can you do with them? Can they add anonymity and privacy? Can they simplify the security proofs and use them on Ethereum? So the one case that has come up, which is different from Zcash, is verifiable computation. So you can create a SNARK to do a batch of signatures, where instead of having to transmit all of the signatures and all of the details of the transactions, you can just send the tiny little bits of information that you really need, like the account ID, the amount, and all of this extra data that you need to verify the authenticity of a transaction can be sort of discarded because of the implicit verifiable nature of this proof. And you can see that the more transactions you get, the more data you save. So if we look at if every transaction is 32 bytes and then the signature's another 32 bytes on top of that, at like 250 transactions, you're saving, like 7 kilobytes or something. But that doesn't seem like much, but in reality, it's like a 50% saving, where they've just cut the amount of data that you need to transmit to every node on the network and to store indefinitely. You've cut that in half. But on Ethereum, there's also the gas problem of if you verifying a zk-SNARK costs you, say, a certain amount of gas, and performing a transaction also costs you a certain amount of gas. But there's going to be a crossover point where it's actually cheaper to do a zk-SNARK than it is to do, say, like 75 Ethereum transactions. And as the different proving algorithms have different costs, the crossover point sort of changes a bit. And at the moment, we've got these three different proving systems. You've got the PGHL, which is the Pinocchio one, Groth 16, and then you've got the more recent GM 17. And with Groth 16, it's under 500,000 gas to verify a single SNARK proof, that's something like 75 transactions. But we're trying to make that even cheaper. So if we're trying to push through this EIP 1108, which should reduce the cost of verifying zk-SNARKs even more, to the point where you can verify one in 70,000 gas, and that's like 4 or 5 transactions. And I think if we can get this pushed through, it will be a game changer for Ethereum rather. But what can you do with zk-SNARK? So the thing that made me sort of see the power of this sort of zk-SNARK hammer is when I compared like a one-event scheme, where you've got the really simple chunk of code there, where you just prove that I am in the set of public keys, and I can generate the public key using my secret for one of those. And instead of having a like complex ring signature algorithm, and you can instead write it very straightforwardly, and your security proof is then much simpler because there's less to go wrong. It's also much more accessible, I think. An example of this would be if you look at like signature verification before you've got the Schnorr verification on your running over elliptic curves, and then you've got the sort of proof of pre-image. Because you're using the zk-SNARK hammer that turns everything into a non-interactive zero-knowledge proof, you don't have to really care as much about hiding your secrets or doing things out in the open. You can use much simpler algorithms like a hash function where you just prove that I knew whatever the pre-image of the hash was. But there's another thing that you need to think about, which is who makes the proof? If it's just you making the proof, then you can use whatever secrets you want. But if you've got but you then have to sort of have the burden of the cost of submitting each zk-SNARK proof to Ethereum and generating it yourself. But because we've got verifiable computation and the zk-SNARK proof proves that this third party can't have tampered with your data if they've made a proof with your data, then instead of having these sort of side chains with the staking and having to put a deposit and these sort of games to keep somebody acting fair, you can just have any third party aggregating all of your data together, and you know that they can't modify it, and they are always going to be acting sort of honestly. So that solves an interesting problem as well. But there's a problem with zk-SNARKs on Ethereum, which is everything is linked back to the gas pair. But with Zcash, the set of people who could have submitted the transaction is everybody who's ever used Zcash. But with Ethereum, you've got this account linking your transactions together, unless you use like a relay service or some sort of transaction anonymizing service. So this is like a problem that's going to hinder you whenever you do use zk-SNARKs on Ethereum and you're trying to go for anonymity. But I'm going to go through like some components fairly quickly. Essentially, blockchain's 99% signatures and hashes. And we've got a hash function and a synchronous cryptography like EDDSA or Schnorr signatures and elliptic curves. And you can then combine them to make authenticated data structures. And apart from what Dara mentioned with the recursive SNARKs and recursive verification, most applications are only going to use these sort of three things. So one of the problems with zk-SNARKs is you need to use a Merkle tree for any situation where you've got even a small amount of data that you're working on that might change every time it's run. Because you can't, ZK or the SNARK circuits themselves, they don't have memory, they don't have sort of persistent state. So your only options are to put all the data into the SNARK and hashes and verify that the hash matches so you know it's running on the correct data, or to use authenticated data structures like Merkle trees. The problem is you are going to have to keep a separate database which keeps track of the content of this, otherwise you'll lose access to your Merkle tree. And of course, for Merkle trees, if you're going to be doing a lot of data access, you need a hash function. But as Dara mentioned, SHA is very expensive inside of zk-SNARK. So one of their main efforts for the next iteration of Zcash was to find a much cheaper hash function. And there's actually another candidate here called Mimic, which is sort of marginally cheaper than the elliptic curve-based Pedersen hash function.
The new proposal that I was talking about,
it's even cheaper.
It's much cheaper.
It's very secretive, though.
It will probably be published in a couple of weeks.
You write it on a napkin and leave it somewhere by accident.
Accidental.
Yeah. But of course, we're doing everything on Ethereum, so you've got the other problem of whatever you write a circuit for, you've got to be compatible with your smart contracts, which is a slightly different problem because Pedersen hash, while really cheap in a zk-SNARK circuit, is very expensive in EVM. And you see you've got the gas limit there, and Pedersen hash quickly exceeds that, and SHA is very cheap on Ethereum. So you can either be slow in the circuit and fast on Ethereum, or you can be sort of not a little bit expensive on Ethereum, but very fast in the circuit. And if we're talking about the difference between a circuit taking like 5 minutes and 1 minute or 10 seconds to prove, if that's the main sort of problem or adoption of your product, then you want to go with like Pedersen hash or Mimic or something like that. And essentially, there's a couple of different concepts that have come out with how we can string these components together so that they can do interesting things like anonymous tokens. And Zcash is an example of an anonymous token where you've got a Merkle tree, you've got a nullifier, then you've got a proof of pre-emission. But there's also a permission database where you, instead of a nullifier, if you assume that everything's in the open and you don't really care about privacy, you gain verifiable computation, you gain like the inability, or you don't need a trusted third party, for example. So by having a public key and then an arbitrary piece of data, be it like an account balance or maybe like a recursive snark proof of a different type, you can have a lot of, it adds a lot of sort of more generic functionality rather than the sort of purely thing designed specifically for like anonymous tokens. But what I'm really here for, I guess, is to dig more into high-level languages and how you can use them on snarks or with snarks. And I'm picking 4 today, which is Pepper, xj-SNARK, Socrates, and Circom, which are all kind of Ethereum compatible, but they represent different levels of abstraction. So with Pepper, you've got, they're trying to go for full C compatibility. They've got an arbitrary memory model, but it's very, very complex. The circuits are very expensive, and it doesn't give you any of the sort of elegance of being able to use algebraic types. I don't know, the optimizations you can do with constraints. And we've got Circom on the right, which is sort of more direct, well, it gives you access to the constraints themselves, but it tends not to do magic for you, and you have to do the laborious stuff yourself. And in the middle, we've got xj-SNARK and Socrates. But just a highlight, I guess, which is compared to normal programming, every branch is always evaluated. All loops are sort of unrolled, and all the variables are global and mutable, and you've got the weird fields in sort of these 2 parallel words. But for Pepper, you can see it's just C code, and it is technically Ethereum compatible. It's got some optimizations, but all the constraints are hidden from you, so you can't see what it's doing. There's no sort of native field type. But one of the most unintuitive things about this, you might end up changing like 3 characters in your program, and instead of it generating 10,000 constraints, it's generating like 500,000 constraints. So because it's hiding everything from you, it can be very unintuitive where you're not sure what it's really doing. And because it's not really C, anything you knew about C kind of doesn't really translate to this. Then you've got zk-SNARK, which is probably my favorite in terms of they've got very, very good optimizations. So an example of this is you can do arbitrary fields with moduluses. So you can do like RSA. Somebody implemented a SecP256, so you can verify a Bitcoin block header, I guess, in a zk-SNARK, which is really, really cool. It's also maintained, but it requires IntelliJ to develop anything with it. But this is kind of in the middle, and it's really cool. Then you've got Socrates, which Dara mentioned as well, which is fairly straightforward. It doesn't really give you constraints or access to the constraints, but it lets you take a Pythonish code, which looks really straightforward. You've got a bunch of nice libraries and sort of packages for it. You've got arrays and structs and everything you'd expect from a programming language. And it's all integrated into this sort of single unit that has a prover. Then you've got Circon, which is sort of more low level. It's JavaScript. You can plug it into your node dependencies, and it just works, and it works in the browser as well. So I'm going to sort of zip through this relatively quickly because it's getting dark. But yeah, so the compiler sits in this graph. So here we're translating the program to the circuit. And what I'm really trying to get to is like code generation, and I guess machine code here would be R1CS. I guess the first step you want to think about is translating this sort of imperative programming language that you're used to into a sort of circuit representation, where you can see where we add to A, instead of overriding A, we just create a new variable, which is A plus C, whatever it is. And instead of loops, we have to sort of unroll them. So you can't have an arbitrary loop or a while loop with some sort of condition to exit, because you need to know exactly how many iterations it will go for. And this kind of comes back to functional programming quite often if you start looking at it as a graph, because you see you've got the reduction of the add function over the array of x's, which produce an array of y's, and you take the last one, which is the sum. And really this comes down to if you are compiling things, you're going to be translating them into constraints. And this is where I cut a bunch of stuff out, because I think Dara's covered this fairly very well, I guess. But with any within this graph, you want to find these points where you need to verify that that sort of node can't be any other value than what you expect it to be. And I guess. And sort of, if we take the example of curve point addition, where the naive implementation is you've got like 7 constraints. This is all just really standard compiler stuff, where you've got your expression that you can represent fairly trivially. And then you've got the common sub-expression elimination. And then you've got maybe some like optimizations which are specific to SNARKs. But none of this is like too different from what we know. It's just with SNARKs we're going over this problem again from scratch instead of being able to use like all of the compilers that already exist. So while LLVM does this already, and it does some like constant folding, common sub-expression elimination. The problem is that we're reinventing the wheel, I guess, and we can't just plug LLVM into this magic SNARK compiler because of the massive fundamental differences we've got.
I think actually LLVM can't do the kind of optimizations I was talking about where I reduce this to 6 or 5 constraints.
No, it can't. No, but it should be able to give you 7 constraints.
Oh yeah.
Yeah.
It's kind of opaque to the optimization you can use the map for, but if it's a graph, you can optimize on a graph.
So
I'm not saying that the optimizations I did by hand couldn't be done automatically. If they can.
But yeah, possibly at some point in that. Right now, no, absolutely.
that's a really good question, actually. But I guess we've got this big graph here that's sort of not really relevant. But if we look back at this, that maybe there are some optimizations that we can do specific to compilers or rank 1 constraint systems where we're going to have to look at it as a graph. And instead of Dara spending like 3 or 4 months sitting there, I don't know, I'm going through like paragraphs of raw constraints, just wondering how, what is this person smoking?
You should share publicly.
but yeah, if we could save all those lessons and somehow be able to apply them to spit out constraints that are in the most optimal form, then that's something that's very unique to zk-SNARKs and to R1CS in general. And all of the work that we do there, we will also benefit if we apply it to bulletproofs and other verifiable systems. So some examples. There aren't that many examples of zk-SNARKs on Ethereum using high-level languages. A couple of people are using Bellman, using EthSnark. But these projects, the one that seems to be picked up a lot was the Circle project, where it's really easy to add it into your node, your npm config, and hook it up into Truffle, and people seem to be picking it up really quickly. So if I say that's the easiest one that's most accessible at the moment, if you know any other, please let me know. And if you are starting, generally these are the 4 different choices you've got. XJ-SNARK, Zilkh, Circle, and Pequin. If you want a high-level language and maybe you're not confident with Bellman or with Camel or coding C++ directly, and we're really looking for more stuff to research and to improve these projects. So implementing algorithms that are compatible with both EVM and the zk-SNARKs, and as I said, optimization and lots of different components. And that's me finished. If you want the slides, they're on the link there. So thank you.
Harry, can I ask? Sure. So your thesis is essentially that if we were to think, there are 2 things I wanted to highlight. I just want to be sure I'm getting you right. So imagine you had an EVM construct that's more kind of SNARK friendly. I could probably say we could have optimal gas utilization. Can I say that?
Yeah. So if you had a built-in instead of an SHA built-in, you had a Edison hash built-in.
Pretty much, yeah. And the second thing you're highlighting is like if you could think of the whole thing as a set of graphs, like we have compile optimization for DNFs in that sense, you could actually optimize this in an automated way. So it's like if you think of the evolution of assembly optimization over time, the improvement we had, we could probably have similar, at least orders of magnitude of improvement. Is that what you're kind of suggesting?
A lot of assembly optimization is really convoluted and not immediately obvious to the compiler. So, 70% of optimizations in like the big tool chains like GCC, LLVM, they're really simple heuristic rules that have been around since the 1950s and 60s, where the first step is break it down into a single static assignment, create a graph, do register allocation, maybe a few small hacks.
Shall we convert her into a heuristic?
And then the remaining of them are just the little lessons, like template matches, right? Sorry.
So you can split if you consider the kind of optimizations that we did in Sapling and that I've been doing recently on recursive validation, that you can kind of split them into two categories. Actually, can I have a... You can kind of split them into two categories. There's stuff that a compiler certainly could do because they're just taking advantage of local arithmetic identities. So that's optimization of the elliptic curve addition, for example. A compiler can definitely do that.
Easily do,
You won't invent Montgomery curves.
No. So if it requires some kind of creativity, as sort of noticing that there's an isomorphism between Edwards curves and Montgomery curves, and you can change representations, and also you need to prove this other bunch of stuff and restrict to the prime order subgroup. No compiler is ever going to be able to do that until we have strong AI.
That's a separate problem.
It's AI complete problem.
Maybe the last question. If anyone has another question. If not, okay. Then can we get another round of applause? I think it's just going to give last words.
Hi, just a few closing remarks. So my name's Ali Benawi. I'm the founder and CEO of a company called Apply Blockchain. We're based here. Some of the teams at the back here. And it's really been an honour for us to be involved in this and to have Harry and Dara here speaking on the subject. I wanted to give a little bit of a practical view of why people like us are interested in this. So we've been building blockchain apps for about 3-4 years now for different clients. So we're kind of at the practical business application end of this. And one of the things that's really been bugging us all this time is privacy and data privacy. We've never really felt that there's been a good enough solution to apply to the solutions that we've been building using blockchain. And we tried to solve some of this ourselves before we came across zero-knowledge proofs, and we didn't really get to the place that we were happy with. And now that we've become more familiar with the technology and the work that was done on Zcash, we realise that actually this is the way that this can be solved. So we've been doing a bit of work ourselves in this space as well, at a much higher level. And I guess at the more practical end of it, looking at the applications that we've already built and how we can apply this to those. But that's really why we're interested in it, and I guess the angle that we're coming at. So yeah, that's it. The project we're working on is called K0, and we're going to publish it and open it fairly shortly as well for anyone who might be interested. I want to say a few thank yous. So first of all, thank you to Alex, who you saw at the beginning, Lewis, who's not here, and Zach, who all helped organise this event here. Special thank you, of course, to Harry and to Dara for giving us their time. Obviously, greatly appreciated. And just to thank you all for coming here tonight and making the event special. Thanks a lot.